Welcome back to Advanced Control Theory lectures. So we will continue with the problem session. So here the next problem is, consider the system described by the equation x1 dot equal to x2 minus x1 into x1 square plus x2 square and x2 dot equal to minus x1 minus x2 of x1 square plus x2 square. We have to assess the stability of this system using Lyapunov theorem. So here you can easily see that these equations are nonlinear systems. So if these type of equations or nonlinear equations are given, you can directly take the Lyapunov second method or Lyapunov direct method for assessing the stability using Lyapunov method. So if the system of equations are nonlinear equations, you can assess the stability using Lyapunov direct method or Lyapunov second method. So as in the previous case, we have to select a positive definite Lyapunov function v of x. So I am selecting v of x is equal to x1 square plus x2 square. As I have already told, you can select for almost all the problems, you can select this as a Lyapunov function. Now find the partial derivative of v of x, that is Lyapunov function. So it will be 2x1 x1 dot plus 2x2 x2 dot. Now for substitute x1 dot and x2 dot. So substitute for x1 dot from this equation and x2 dot from this equation. So if you substitute, we will get an equation like this. V dash of x is equal to minus 2x1 raised to 4 minus 4x1 square x2 square minus 2x2 raised to 4. So here we can take minus 2 outside and the equation will become minus 2 into x1 raised to 4 plus 2x1 square x2 square plus x2 raised to 4. So we can rewrite this equation as v dash of x is equal to minus 2 into x1 square plus x2 square all square. So we got v dash of x. Now we have to find whether this is a negative definite function or negative semi-definite function. So here you can see that this is a negative definite function because for all the values of x1, x2 except at origin, that is except at 0, 0, this equation will give a negative value. So if you substitute 3, 0, 4, 0, 2, 5, minus 3, minus 8, etc., any value except origin, this equation will have a negative value. Hence, this v dash of x is a negative definite function, or v dash of x is having a value less than 0 except at origin. Hence, v dash of x is said to be a negative definite function. Please go through the sign definiteness. What is sign definiteness and what are the criteria and for sign definiteness. Now we got v of x as, we have selected v of x as a positive definite function and we got v dash of x as a negative definite function, and hence we can say that by Lyapunov stability theorem or by second theorem we can say that the equilibrium state at the origin is asymptotically stable. The Lyapunov theorem for asymptotic stability is that, suppose the theorem is described by x dot is equal to f of x comma t and f of 0 comma t equal to 0. If there exists a scalar function v of x having a continuous first partial derivatives and satisfying the conditions like v of x is a positive definite function, v dash of x is a negative definite function, then the equilibrium state at the origin is said to be asymptotically stable. That is Lyapunov theorem for asymptotic stability. Please go through theorem part. So we got v of x as positive definite. We selected v of x as positive definite and we got v dash of x as a negative definite function. Hence we can say that the equilibrium state at the origin is asymptotically stable. Now in addition, if you take norm x tends to infinity, this is Euclidean norm, and Euclidean value of a vector x is equal to square root of x1 square plus x2 square plus etc. up to xn square. So if this norm x or Euclidean norm tend to infinity, we can say that the x1 x2 values tend to infinity, we can say that v of x also tends to infinity. Hence this condition satisfied here. Hence we can say that the equilibrium state at the origin is said to be asymptotically stable in the large. Since this condition is satisfied, we can say that the equilibrium state at the origin is asymptotically stable in the large. So when you got v dash of x is negative definite, when you got v dash of x as negative definite, you have to check additionally you have to check this condition as well. So here by Lyapunov stability, we are saying that the equilibrium state at the origin is asymptotically stable in the large. Now the next problem. Consider the system described by the equation x1 dot x2 dot equal to 0, 1, minus 1, minus 1, x1, x2. Check the stability of the system using Lyapunov stability analysis for linear time invariant system. Here we can see that this system is a linear system. This problem we have already discussed using, in the first lecture we have already discussed this problem, but in that question we have approached this using direct method or Lyapunov second method. But here in the question it is specified that assess the stability using Lyapunov stability analysis for linear time invariant system. So for linear time invariant system, the condition to assess stability is somewhat difficult. So if this part is not given, if this part, that is Lyapunov stability analysis for linear time invariant system is not given, you can, if it is not given, you can continue the analysis as in the previous lecture, that is lecture 1, Lyapunov stability lecture 1. But here the approach is somewhat different. So we can write the equation of, we can write the state equations x1 dot and x2 dot. For this system, we can find the equilibrium state of the system. For finding the equilibrium state, you have to equate the derivatives of state variable into 0. So equate the derivatives of state variables, that is x1 dot and x2 dot equal to 0. When x1 dot equal to 0, that means sorry, there is an error here. It is x1 dot is equal to x2. It is not x1, it is x2. Sorry, here this is x1 dot is equal to x2 and x2 dot is equal to minus x1 minus x2. Sorry, here this equation is x1 dot is equal to x2 and x2 dot is equal to minus x1 minus x2. Now if you substitute for x1 dot is equal to 0, x2 will become 0 and x2 dot equal to 0. Since x2 dot equal to 0 and x2 equal to 0, x1 will be also 0. Hence we can say that equilibrium state is at the origin. Now coming to our problem. Here for linear time invariant system, you have to select v of x as a quadratic form, that is x transpose px, where we know x is a column vector of x1, x2, x3, etc. up to xn. Like in the case of state vector, x is a column vector, and by derivation there is a derivation for finding v dash of x. Or by derivation, v dash of x is equal to minus x transpose qx, minus x transpose qx. So we know for asymptotic stability, this v of x should be a positive definite function and v dash of x should be a negative definite function. And for the linear systems, in the case of linear systems, if the origin is asymptotically stable, it is also asymptotically stable in the large. So here from the derivation we will get a transpose p plus pa is equal to minus q. This is for finding the stability or finding the stability of a linear system using linear time invariant system using Lyapunov method. So you will get this equation. The detailed derivation is given in the material I have shared with you, ACT module 5,6. The derivation is there. Please go through the derivation. So, for linear time invariant system, we have to take A transpose P plus PA is equal to minus Q. And Q should be taken as a positive definite matrix. The equation is A transpose P plus PA is equal to minus Q. Q should be taken as a positive definite matrix. When Q is a positive definite matrix, here in this equation V dot of x equal to minus x transpose qx. This will be a negative definite function. When q is positive definite, this equation is multiplied by a negative sign here. Hence, this v dot fx will be a negative definite function. So, for these type of problems, write the equation A transpose P plus PA is equal to minus Q. Take Q as a positive definite matrix. So, here for simplicity, I am taking it as an identity matrix. All identity matrices are positive definite matrices. So, 1, 0, 0, 1. Or you can take the principal minor. First, this 1, its value is greater than 0. Then take the determinant of this whole matrix. Its value will be also greater than 0. Now, let us assume P is equal to, since this is a 2 variable equation, the equations are of a 2 variable, or A is second order system. A is a second order system, or A is of 2 by 2 matrix. Your Q and P all will be 2 by 2. Since A is 2 by 2, or this is only having 2 variables, state variables x1 and x2, your Q and P all will be having the order 2 by 2. So select P is equal to P11, P12, P21, P22. As in we are discussing about the quadratic form, we are already discussed about how to get the Hermitian matrix from a quadratic equation. So here this P matrix is a Hermitian matrix, hence P12 equal to P21. Since this is a Hermitian matrix, P12 equal to P21. Now we have to find the value of P11, P12 and P22. That is the next step. For that, substitute here in this equation, that is A transpose P plus PA is equal to minus Q. A, it is given in the question as 0, 1, minus 1, minus 1. So find A transpose. P should be taken as this, A transpose into P plus P into A. That is equal to minus Q. Since Q is identity matrix, minus Q is minus 1, 0, 0, minus 1. Now, find the matrix, find the product of these two matrices, add it, then we will get final matrix like this. Equate this into this minus Q or minus identity matrix. So, from this equation, we get minus 2 P21 is equal to minus 1. P21 equal to 1 by 2. P21 equal to P12 since P is an Hermitian matrix. Now 2 into P21 minus P22 equal to minus 1. From this P22 equal to 1 and substitute here in this equation, that is P11 minus P21 minus P22 equal to 0. We already have the values of P22 and P21. So by substituting this, we will get P11 as 3 by 2. So our P matrix is 3 by 2, 1 by 2, 1 by 2 and 1. So we got the P matrix. Now the next step is, we have assumed Q as positive definite matrix. Then we have to substitute in the equation A transpose P plus PA is equal to minus Q. For that, V of x should be positive definite and V dash of x should be a negative definite function. So from this, we have to check whether our P matrix is a positive definite matrix. When the P matrix is positive definite, then only our condition for stability will match. So check whether P matrix is a positive definite matrix. So for checking, we have take all the principal minors, like 3 by 2 is greater than 0. Then take the determinant of the matrix, this is also greater than 0. Since all the principal minors are greater than 0, P is a positive definite matrix. And we can say that equilibrium state at the origin is asymptotically stable in the large. In linear time invariant system, when the equilibrium state is asymptotically stable, we can say that it is asymptotically stable in the large. I am sharing the materials for this or the notes I am sharing in the Google Classroom. Thank you.